Hello, hello, hello. Today we still got potential. This will be the part 3, last part of our potential series. Remember the last video, we want to remember 2 key things. Number 1 is let me grab my pen, voltage. The definition of voltage is the difference in electric potential. You can understand electric potential as a value, a calculated value between 2 locations. And 2, opposite attracts. Yes, opposite attracts. And the same repel. Yes, repel. And so we are mainly going to talk about membrane potential, specifically resting membrane potential and action potential in this video. And I know it is a short introduction to neurons and the fire and the wire and the transmitters and the binding and everything. But I promise you there will be further videos to help you understand more. And so we have a neuron here, and it got beautiful dendrites and the cell body, soma, and the node of Ranvier, pronounced by the French. And we have the myelin sheaths here, axon terminals. And let me be clear, we will not talk about the node jumping of action potentials in this video. We're just going to look at a simplified version of how action potential travels and what is actually traveling. And I will make a separate video on the difference between myelinated neurons and unmyelinated neurons and why myelin sheaths is so magical. And if you love that idea, please leave me a comment and I will make your wish a reality. And so today, let's look at this diagram here, right? I've combined the 2 diagrams into one. So 1 and 2, and don't worry, I'll share the diagrams. I'll share the whole board when I'm posting part 3 of potential. And so that you can save it, if you're a visual learner, that helps you. And also these images, if I don't have any citations, is generated by ChatGPT Plus. And ChatGPT, if you're watching this, please considering sponsor me. Thank you. So, okay. There's something missing about this chart. ChatGPT is not perfect. So let's say we have, this is a very average drawing, but let's say we have something of the neurons receptors and the neurotransmitters are binding into the receptors. Imagine there is something like that in the way front of this membrane, right? Basically, this part is representing the axon on this picture, right? So just in your head, translate that. Here, this part equals this part. That's it. And we have some, let's say currently my cats are chasing a fly. And so let's say my cat's seeing the fly, my cats want to chase the fly, and it's going to cause, I'll try to pronounce this word, aceclonine. Acetylchlorine. I'll just call it ACH, to bind to the receptor here. You can imagine any neurotransmitter here. So we bind it, right? And what lectures usually talk about is, okay, we have the resting potential, which is about -70. And we have the threshold, which is -55. And for the moment, a lot of people will talk about, okay, outside is very positive. right? Outside the membrane. And inside is very negative. And inside is full of potassium and outside is full of sodium. And hence one lecture, I'll post that link when I post this video as well, ask us to imagine a salty banana, which I think is quite funny and really helps me understand it. But the one question I have is, if you notice, both the sodium and the potassiums are positively charged. And if you look at a simplified diagram, some people will do like this, and plus outside, and just label the sodium and potassium here. I start to go crazy because then I remembered what's the lesson we need to remember from the last video, is that the same repels, right? Why wouldn't the membrane be pushed around if both are positive? And later on, I did some research. It turned out that it's not just the sodium and potassium. Inside the membrane, there are some negatively charged ions. And so, hence, inside is negative, and outside is positive, apparently. And why it has to be minus negative 70 currently, I don't know. I just take it for the face value. Someone must have done some research, and it is how we live. Our neurons, resting potential, negative 70. Boom, there is that. And then when a lot of positive, say the ACH is very positive, when a lot of positive ions get into binding into the neurotransmitters and get into the membrane or the axon, what will happen is this will become very, 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 very positive. And hence it will trigger this action, which is the from phase 1 resting potential to phase 2 depolarization, and then maybe peak. But depolarization is actually a very important phase because we have a threshold minus 55. Why it is minus 55? Don't know. Didn't ask. Someone have done research on it. So basically, if it's minus 55, boom, we fire. And if it is not, maybe it hasn't reached 55, we're just like, did it really happen? No, not really. Did it fire? No, it did not fire. We just like kind of let it go. So, all right, back to the resting potential depolarization. And you notice there are two different colors of gates. If you want, you can imagine that as like a shopping center or like a supermarket. In Australia, we have Woolies and Coles. And imagine like one is to get in, one is to get out. Let's think in this way. And so what would happen is when this becomes overly positive, basically they will be opening the gate, and then the sodiums will rush in, and then it becomes very positive, and then the sodium then becomes inactivated, cannot open. The membrane potential is still positive, and then the potassium channel would open and flows out. That would call depolarization. Potassium out to keep the balance, and then the inside would become negative and negative and negative again, until the gate is closed. And when I'm looking at the diagrams, and I Googled a lot of diagrams to understand what is actually firing and what it is action potential, I seriously didn't understand it. But what has happened is that normally we would imagine this is kind of like this. We got something, we did something, travels towards the end and go to the next neuron. And actually, it is not. It is not like a straight line. It is more like a wave. It's more like if you remember the last video, it's more like a wind. But it's more like if you want to think about it as an ocean wave, that is also okay. But let's go to a space here. So what actually happened was there was a transmitter, there was neurons binding, and then becomes very, very positive, very, very positive. Guess what? In the same membrane, the same axon, the next part is negative. So what's going to happen is going to travel towards the next section, and this section would become positive. The voltage would then travel again. That section was actually very negative and attracted again, and then becomes positive, and then same happens. So it's more like a wave. You travel, you travel, you travel, you travel in this way. It is not a straight line at all. So for me, it is very hard to give a definition of action potential. And what I can say after my own research is that it is a voltage charge traveled through the membrane section by section, or you can think of it as patch by patch, by which we can monitor the travel by these 5 phases and this membrane potential graph. And that's kind of it. Let me know if it is helpful for you to understand the membrane potential, or like how we fire action potentials by this video. If you have any questions, comments, please don't be shy. Write to me below. Until then, I will see you next time.